This is the first in a series of lectures about regression, and we're going to start off pretty simple, talking about basic least squares. So the goals of statistical modeling are to describe the relationship between variables or their distribution, and then maybe to make some inference about either the distributions or relationships that you've described. This first lecture is going to talk primarily about these first two things, describing the distribution of variables and describing the relationship between variables. In future lectures, we'll be talking about how to make inferences on those relationships. The data set that we're going to be using is actually kind of an old one. It was collected by Francis Galton. And the data set was collected to show that you could actually predict the height of children by averaging their parents' heights. So on the x-axis, what you have here is the average parent height, what he calls the mid-parent. And on the y-axis, you have the child's height. And so you can see that there's actually a very nice relationship between these two variables. Now this seems pretty obvious to us now that tall parents have tall children, but it turns out it wasn't so obvious when he did this hundreds of years ago, and so it was actually kind of a big deal, and it actually was one of the earliest examples of regression analysis. And it's still actually a relevant problem. So this is sort of a little bit of a clever, funny paper where these investigators predicted the height of children based on the mid-parent height. That's the Victorian approach, which was the approach that Galton developed. And then they also used the latest genetic measurements that they could get their hands on, the best genetic measurements we have for predicting height, and made predictions using those measurements as well. And it turns out that it's still better to just predict using the average of the parent's height, what your height will be, rather than using genetic information, even with all the modern tools that we have. So it's still sort of a relevant problem to be considering. You can load the data into R from the using R package. So if you load that package and then type data of Galton, you'll actually get the data set. And you can look at a histogram of the children's heights and a histogram of the mid-parents' heights. And these distributions look sort of fairly nice and symmetric and normal looking like this. And so one of the things that you first might ask yourself is when you're looking at this sort of distribution of children's heights is how would you summarize this distribution? And in particular, one question that often comes up is, if you had one number to summarize this distribution, what number would you use? And so the number that a lot of people would choose, and then when you have a symmetric distribution like this, a number that's very, very good choice is to use the mean. So here I've again showed the histogram of the children's heights from this study, and then I show in this red bar here the mean value, which is about 68 inches. And so this is a pretty useful choice of a number to report because it tells you a little bit about where the distribution is centered. And so it actually also is optimal in a particular sense. So one reason why the average might be a good number to report is that it minimizes this set of errors. So suppose that we have a child's height labeled as CI, and we have 928 of those heights in this Galton data set. And so we can look at the difference between that variable CI and one number, the number we're going to use to summarize the data set, and we can square it up so that negative or positive differences from that number contribute the same amount to this total error term. And it turns out the average is the number that minimizes this quantity. So it has a nice theoretical justification as well as being sort of a sensible thing to do in terms of reporting about something about the center of the distribution. So if actually we knew a little bit more information, say we knew the mid-parent height, we might be able to have a little bit better prediction or a better summary of the child height distribution. So here what I've done is I've plotted that scatter plot of the mid-parent height versus the child height. And you can see it has this sort of nice sort of oval shape, and that there seems to be a relationship between the two variables that we might be able to use to tell us a little bit about the distribution of child's heights. And so the first thing that I would point out though is that each of these points doesn't represent just one point. There's actually, these points are kind of stacked up on each other because Galton didn't record height to many significant digits. So you can actually jitter the data. This is actually, I'm showing you this mostly so that you can see how this jitter command works. So what jitter does is it actually adds just a tiny little bit of random noise to a variable. And so I've added just a tiny little bit of random noise to the parent variable and a tiny little bit to the child variable. And you can see these points that were just dots before have now kind of smushed out, so you can see how much data is here in the center of the distribution versus how many points are out here on the edges. So the thing that we could do is we could actually look at a number of different ways of predicting the child's height from the parent's height, but one way that it makes a lot of sense is we could start with, okay, so suppose that we know that the average parent height is 65 inches tall, then what is the average child height for parents that have that average height? And so you can see here, for example, that the child height is a little bit taller than that. It's about 66 inches is the average height for children who have average parents of 65 inches tall. And then what we could do is actually look at a different part of the distribution. We can look at, say, for the tall parents, what does it look like? So here we're saying, suppose that the average parent is 71 inches tall. What do their child's heights look like? And here you can see that the average child height is actually just a little bit lower than that. It's only 70 inches. But you get sort of the average of the distribution for that particular set of heights. So another way that we could summarize it is we could actually draw a line. And so here's a line that you could draw through the distribution that tells you something about if you are a parent height, an average parent height of 66 inches, what is the average child height that we would predict for you? And so here's a line that you could draw, and this is the line that you get if you use the LM function. And so what I've done is I've fit what's called a linear model, and this is going to minimize, you'll see in just a second, another least squares or sum of squares problem. And so what I've done is I've said, okay, that the outcome variable here is the child's height. That's the y-axis is going to be the outcome variable. And then I say tilde and then the parent height. And so the parent height is the covariate that we're going to be fitting. And so I'll explain what equation that this LM command fits in a minute, but essentially the key thing to keep in mind is that you're going to be putting the outcome in particular for LM, usually a quantitative outcome on the left side of the tilde, and on the right side of the tilde, all of the variables that you're going to be including in your model. And so a question that comes to mind that's pretty obvious is why not use some other line? Why did we use that red line that we showed just a minute ago? And it turns out that there's a reason that's very similar to the reason that we use the average to summarize the distribution. So you can remember from your middle school or high school geometry class that the equation for a line relating the child's height to the parent's height would be something like this. You have the child's height is equal to some intercept term, so this is where the line crosses 0, plus some slope times the parent height. So this would be true if all of the child's heights and parent's heights fell along a specific line. But of course that isn't exactly true, right? We see the line here that's going up from left to right, and we see that the points don't exactly fall on that line. There's actually some variation around the line that occurs. And so we can actually make this equation a little bit more complicated, but not too much more complicated, by saying, okay, here's the equation for a line, the intercept term plus the slope times the parent height. And we're going to say, well, we've added what we're calling an error term here, where again, remember, EI represents everything we didn't measure. So in addition to measuring, it could be just measurement error, they didn't measure the heights very well, or it could be we didn't know how much a particular child was eating, where they lived, whether they stretch in the morning, whether they're healthy or sick, and all of that information might contribute to the child's height above and beyond what we know about the parent's height. So once we have an equation like this, we might think about, okay, well, now how do we fit that line? How do we get the best line here? And it turns out that the best line that we're going to pick comes out to be a solution to a similar sort of problem that we had before. So we have the child's height, and that's the height that we're sort of trying to guess or predict. And we want to be able to estimate that based on something about the parent's height. And in this case, we're going to be using this line. So we have this equation for the line, and we could just pick the B0 and the B1 that make the distance between our equation for the line and the child's height the smallest. And so when you use LM and R, it's actually just doing this. It's solving this equation to get the value of B0 and B1 that make this sum of error terms the smallest. And so again, what you can do is you can actually fit that term in R, and then what you can do is you can plot the parent's height versus the child's height, and you can add on top of that the fitted values. So the fitted values are the values where we actually know what B0 and B1 are, because we fit them with this least squares problem. And so what we can do is we can actually plot the line that is our estimate of B0 plus our estimate of B1 times the parent height, and that's going to represent just that straight line, and we can plot that on the graph here. And then we can actually calculate the distance from each point down to the line. So the distance from this point to the line, the distance from this point to the line. And that tells us a little bit about how much variation there is around the ideal case where the average parent height would be exactly equal to the average child height on this line. Um, and so what you see actually here then are these what we call them residuals, which are the differences between these points and the line. And you can see that they're centered at 0 now because we've subtracted off the best fitting line, and those points are actually sort of distributed like a cloud around that line. And so in the next lecture, we'll see how we can use this variation that we've got left over after we fit the line to actually make some inference and determine what's going on in the larger population.